Hello dear students, in today's lecture we will try to understand the role of magnetic field in plasma diffusion. So, in continuation to our discussion so far, we have learnt diffusion will depend on many things. It will depend on the collisional frequency, it will depend on the mass, it will depend on the temperature, and the primary role of diffusion can be to negate the concentration gradients, and in the process the collisions will happen. And there are situations in which collisions may not actually be relevant. Okay. So, we have to understand if you take plasma and if you are trying to understand diffusion processes, we can see plasma in a broad characteristic as one with collisions, the plasma in which there are collisions, or we can call it as collisional plasma, and another type of plasma can be collisionless. So, if you recall our earlier discussions, there were some situations when in the absence of collisions there will be no energy transfer that happens from one point to another point, and the wave motion can have any velocity, it can even be greater than the speed of light, right. So, things like that, and there can be some plasmas in which the plasma is, if it is collisional, then you can have a fully ionized plasma or you can also have a weakly ionized plasma, fully ionized plasma or a weakly ionized plasma. So, in fully ionized plasma, you will have Coulombic interactions, and in weakly ionized plasma, you will have collisions with the neutral species, right. So, at the beginning of all these discussions, we know very well that the particles or the plasma as a whole is highly subjected to a magnetic field. I mean, the magnetic field can have a profound influence on the way plasma particles move. Now, the movement is what is represented by the diffusion, or diffusion actually talks about movement or what happens in this movement as it collides, as the particle collides, right. So, now depending on the primary classification that we have just talked about, so plasma's collisions can happen in all these different types, and diffusion is a very essential part of that. So, since the particle's movement is highly influenced by the magnetic field, it is natural for us to expect that diffusion will change by the application of magnetic field. So, why do we even talk about this? Because it is a central problem of thermonuclear fusion. If you are trying to solve problems or devise applications or in research related to thermonuclear fusion, this is the central problem, how to handle diffusion or how diffusion changes with the external magnetic field. So, to study the effect of magnetic field on diffusion, we consider a weakly ionized plasma in which electrons and ions are non-uniformly distributed across the length of the plasma confinement and in the constant background of neutral species. So, what do we consider? Weakly ionized plasma, weakly ionized plasma. So, that means there will be a lot of neutral species, in the background. Okay. And non-uniform distribution. Why do we call or we bring this non-uniform distribution into the picture? Because if there is no irregularity in the distribution of plasma, then there is no provision to have this pressure gradient or the diffusion to happen. Okay. So, since the magnetic field does not affect particles' movement in its own direction, if the particles are moving in the direction of magnetic field, the magnetic field cannot have any influence on those particles, right. So, we will consider the magnetic field to be in one particular direction and we will try to see what happens in the directions perpendicular to this magnetic field's direction. Primarily, we will be looking at how the diffusion coefficient dA. What is diffusion coefficient? It is kBt by m nu. How this will change as a function of magnetic field or in the presence of magnetic field, or how the mobility will change as a function or due to the presence of magnetic field. So, it is natural for us to expect that these two parameters will not change in the direction of magnetic field, rather they will change in the perpendicular directions, right. So, now at this point, in the presence of magnetic field, due to collisions, what will generally happen is that the particles, due to collisions, particles will diffuse across the magnetic field into the walls. Okay. So, to see how this is this can be understood or how this comes about, we can basically start with the basic fluid equations. So, the basic fluid equation contains the rate of change of velocity on the left hand side, and on the right hand side all those parameters, all those force terms which will balance the rate of change of velocity on the left hand side. So, the equation is very familiar to us. We have written this equation so many number of times. Du by dt is plus minus, m is the mass, n is the number of particles per unit volume. So, this becomes the density actually, plus minus En times E plus U cross B minus del P minus Mn nu U, right. So, this term is the Lorentz force, this term is the pressure term, and this is the collisional term, right. Now, all of these things can of course have an influence on the movement of the particle. Now, this after this the mathematical treatment is basically rigorous algebra, but otherwise it is very simple. Now, this can be done by neglecting the electric field altogether. We can consider only the magnetic field. We will still be able to arrive at the conclusions, but let us see how we proceed by including the electric field also. Okay. So, now assuming that the deviation from the equilibrium, from the stability due to the inhomogeneity in the number of particles per unit volume or non-uniform distribution is to be very small. So, assuming that the deviation from the equilibrium due to the concentration gradient to be very small, we can assume a steady state. We can say that the steady state exists and the rate of change of velocity in this case will be 0. So, pressure P can be written as N kBt. Using both of these things, you can write 0 is equals to plus minus En E plus U cross P minus kBt del n minus Mn nu U, or we can conveniently write by bringing the frictional term or the collisional term here, Mn nu U is equals to plus minus En E plus U cross P minus kBt del n. Okay. Let us say we call this equation as 1, this as 2. So, we will assume the magnetic field to be, let us say, in the z direction. Okay. Now, this is familiar to us, and you will assume the electric field to be Ex, Ey, Ez. So, given these two things, we can break this curl and write 3 component equations from equation number 2 itself. This is a very familiar exercise that we have done earlier multiple number of times. So, with that I will directly write the equations and you can derive it at your convenience. So, we can write Mn nu Ux is equals to plus minus En Ex plus minus En Uy Bz minus kBt dou n by dou x, or Mn nu Uy is equals to plus minus Ey minus plus Nux Bz minus kBt dou n by dou y. Mn nu Uz is equals to plus minus En Ez minus kBt dou n by dou z. So, we call these as 3, 4 and 5. Okay. I hope there is no confusion in this. So, we have just expanded this E plus U cross B and written 3 component equations, and along each direction I have taken the equivalent term which appears in the gradient of the concentration, right. Now, just take the equation number 5, you can write Uz is equals to plus minus En by Mn nu Ez minus kBt by Mn nu dou n by dou z. So, you can cancel n here and you can write Uz as plus minus E by M nu times Ez minus d by n. Kt by M nu is the diffusion coefficient times dou n by dou z, or Uz is plus minus mu Ez minus d by n dou n by dou z, right. So, this equation is familiar. If you go like 2 or 3 lectures before, we have derived a very similar equation in which the mobility and the diffusion coefficient, both of them appear, right. Now, the point that I wanted to make here is that the velocity component along the direction of the magnetic field will depend on, of course, these parameters, but it is unaffected by the magnetic field. So, they will remain a constant. So, we can call these mobility and diffusion coefficients as the parallel components, because they are parallel to the magnetic field. Okay. Now, let us talk about the other 2 equations, which are equation number 3 and 4. We can simplify these equations by sending all the multipliers of Ux and Uy to the other side, and we can write Ux is equals to plus minus En Ex divided by Mn nu plus minus En uy b z divided by mnu minus kbt to dou n by dou x to 1 by mnu. Right. You see this, the velocity component ux has this uy and the other terms. Similarly, uy component has this ux, right. That means that we can use this equation number 4 and we can substitute into equation number 3 and get a solution, a combined solution for all that. Similarly, we can write, or we can simplify this as ux is plus minus ex by mu plus minus eb by mu times uy minus kbt by mnu to dou n by dou x, or ux is equals to, because E by mu is the mobility, we can write ux is equals to mu times x Eb by m. What is Eb by m? Something very familiar to us, which is omega c, the gyration frequency, divided by nu uy. Kbt by mu is the diffusion coefficient, d by n dou n by dou x. This is what is this? This is ux. Let us say we call this equation as equation number 6, and since this is an important equation, we will highlight this. Okay. So, this is ux. In a very similar way, you can also write an equation for uy as plus minus mu ey minus plus omega c by nu. I hope you remember why we are using this symbols of plus minus and minus plus. D by n. Even if you do not remember, you can go back and watch the earlier videos. This will be clear. Okay. Right. So, equation number 6 and 7 are nothing but 3 and 4 written in a clear form. That is it. Okay. Where E by mu, E by mu. This is charge by mass into 1 by time, collisional frequency, and diffusion coefficient is kbt, energy, by mu. And for reference, omega c is Eb by m or Qb by m. This is the cyclotron frequency, not the collision frequency. This is the cyclotron or gyration frequency, cyclotron frequency. Now, we have to solve equation number 6 and 7. Okay, that is the main task. This is simple algebra, you can solve it by yourself. You just have to substitute one term into other and then make some changes, you will get the form anyway. So, the task is to have in the ux term, in the ux equation, you should not have any uy, and in the uy equation, you should not have any ux. So, you have to decouple these two equations and then you will get a solution of this form, which is ux times 1 plus omega c square tau square. What is tau? Tau is the inverse of collisional frequency. So, ux times 1 plus omega c square tau square is plus minus mu Ex minus d by n dou n by dou x plus omega c square tau square Ey divided by b minus plus omega c square tau square kBt by Eb 1 by n dou n by dou y. Similarly, Uy times 1 plus omega c square tau square is plus minus mu Ey minus d by n dou n by dou y square tau square Ex divided by b plus minus omega c square tau square kBt by Eb 1 by n dou n by dou x. It is a very good exercise that you can do this algebra and get these two equations. This is 8 and this is 9. Right. Now, what is tau? Tau is 1 by frequency. So, if frequency tells you how many number of collisions will happen per unit time, tau is the relaxation time. It is time between the collisions or between two successive collisions. Right. Now, you have 4 terms on the right hand side for each velocity. Right. So, we have 1, 2, 3, 4. So, the first 2 terms of the equation represent the mobility and diffusion in a direction parallel to the gradients in potential and density. Ex represents the gradient in the potential, dou n by dou x of course represents the gradient in the number density or the concentration, right. Okay, but they are perpendicular to the magnetic field. The mobility and the diffusion are of course perpendicular to the magnetic field because they are characterizing the movement in x direction which is perpendicular to the z direction. The last 2 terms, if you see carefully, represent the E cross B drift and the diamagnetic drift. Now, if you wonder what are these E cross B drift and the diamagnetic drift, then probably you will have to go back and see the earlier lectures. When you talk about E cross B drift, you are referring to, let us say, the particle description of plasma. When plasma is subjected to simultaneous E and B fields which are perpendicular, it will experience a drift which is called as E cross B drift. And the diamagnetic drift is when you call this particle plasma as a fluid, and then you can get that diamagnetic drift. Right. Now, these 2 things, E cross B drift and the diamagnetic drift, by definition will be perpendicular to the gradient, of potential and gradient in the number density, perpendicular, not parallel. This is parallel to the gradient, see, this is perpendicular to the gradient. Now, with these equations, what we will do is, we will not bother ourselves with the E cross B drift and the diamagnetic drift because they do not tell you anything about the diffusion or the mobility. So, we will confine ourselves to the discussion of only the mobility and the diffusion. So, then we can write the equation Ux as plus minus mu Ex divided by 1 plus omega c square tau square minus d by n dou n by dou x times 1 by 1 plus omega c square tau square, and Uy is plus minus mu Ey times 1 plus omega c square tau square minus d by n dou n by dou y times 1 by 1 plus omega c square tau square. Right. So, this is a modified scenario. We just have everything else pushed to the right side. Right. Now, the mobilities and the diffusion coefficients that we see here are basically perpendicular to the magnetic field. Right. So, we can now define the perpendicular mobility and perpendicular diffusion as mu perpendicular is whatever the mu is there, E by m nu divided by 1 plus omega c square tau square. And similarly, the diffusion coefficient, the perpendicular diffusion coefficient is the normal d divided by 1 plus omega c square tau square. So, what it means is that the diffusion and the mobilities in the perpendicular direction to the magnetic field are decreased by a factor of, they have been scaled down, they have decreased by a factor of 1 by 1 plus omega c square tau square. Now, you see, if you just compare these two equations with this equation, with this equation, you see, this equation has no hint of magnetic field, right. So, the motion of particles will only be dependent on the diffusion, parallel diffusion or the mobility, but there is no hint of magnetic field because the magnetic field is parallel to this direction, right. But if you put this equation in contrast with these two equations, what you see? You see the same form, the basic form is still the same, but everything appears to be scaled down by this additional factor 1 by 1 plus omega c square t square. Now, this scaling or the decrease is only because of Bz. Now, you do not see a Bz here, right, but omega c is qb by m. There it is, the magnetic field is implicitly appearing in this scaling factor in terms of omega c, right. So, this is the basic conclusion of this topic, which is the magnetic field's effect is to decrease the mobility and the diffusion coefficient by this particular factor. Now, when you consider a very strong magnetic field, what will happen is omega c square tau square will become much greater than 1. Omega c is qb by m, the cyclotron frequency. The cyclotron frequency tells you how many gyrations the particle can make per unit time, right. And tau gives the collisional relaxation time. How much duration is required between two successive collisions. So, these two things are exactly kind of opposite to each other. One is telling you how much time it will require between two successive collisions, and another is telling you before one collision what is the frequency of this motion of the particle, right. But when you consider the magnetic field to be very, very strong, so this numerator becomes large, qb by m becomes very, very large. So, omega c square t square will become much larger than 1, right. So, then the d perpendicular, the diffusion coefficient, perpendicular diffusion coefficient can be written as d by, because see earlier it is just a number, all of this that appears in the denominator is just a number because you are adding it to 1. So, it is just a number, it is a scaling factor. Now, so d perpendicular becomes d by omega c square tau square. So, we can write it as d we know as kbt by m nu times tau square is nothing but nu square and omega c square is q square b square divided by m square, which will give you kb t nu m divided by q square b square. Let us see, the d perpendicular is kb t nu m divided by q square b square. The d that we know very well is kbt by m nu. So, you see the difference? The perpendicular diffusion coefficient is directly proportional to mass, and the diffusion coefficient otherwise is inversely proportional to the mass. So, this drift is of course perpendicular to the magnetic field, that is what we have been telling from the beginning. So, the perpendicular diffusion coefficient is proportional to the collisional frequency. So, this is also one more, d perpendicular is proportional to the collisional frequency. The physical meaning of this is because the collisions are needed for plasma to diffuse across the magnetic field, right. Whereas, diffusion in the diffusion coefficient in the absence of magnetic field or in direction parallel to the magnetic field is proportional to 1 by nu. Okay. So, it is because how do we explain this? Because the collisions generally retard the movement, they will not facilitate an easier movement from point to point, right. So, this is the basic difference, the diffusion coefficient proportional to the frequency and the diffusion coefficient proportional to 1 by frequency. So, now if you remember the fact that the collisional frequency is generally proportional to 1 by square root of m, that means electrons diffuse more rapidly than the ions because of their lower mass and higher mobility or higher thermal velocities. So, in a perpendicular diffusion, electrons generally move slower than the ions, right. So, this is some discussion about how particles will diffuse in the presence of magnetic field. Now, what we have seen so far is that it is a weakly ionized plasma in which particles are the diffusion, the coefficient of diffusion and the mobility are strongly influenced by the presence of magnetic field. So, based on these concepts, it is essential that we solve a couple of numerical problems so that we appreciate the physics even better. So, we will consider a simple numerical, question 1. So, let us say in a weakly ionized plasma, characterized by 2 electron volt, mobility is 120 meter square per volt second. Find the diffusion coefficient. Okay. So, we know that d by mu is kBt by E, because d is kBt by m nu and mu is E by m nu, right. So, d by mu, why we use this relation? Why can't we directly calculate the diffusion coefficient? Because we know the formula, but we do not know the mass, we do not know the frequency, right, but mobility is given, right. So, d by mu is equals to kBt by E. So, diffusion coefficient d is equals to mu E kBt divided by E. The temperature in the units of electron volt is already given to us, right. So, d is equals to 120 times 2 electron volts into 1.6 10 to the power of minus 19 divided by the charge again 1.6 10 to the power of minus 19. So, the diffusion coefficient D is 240 meter square per second. Okay, so this is one problem that we can quickly solve based on the understanding between the mobility and the diffusion coefficient. We have one more numerical which can be solved by using the diffusion equation and involving the fact that the density gradient comes into this diffusion equation. Okay, so the problem is you have a question number 2. We have a weakly ionized plasma. The plasma is weakly ionized. So, we are still doing problems which are relevant to topics that we have understood so far. We still have not gone into fully ionized plasma. So, weakly ionized plasma, the slab geometry is given like this. Slab geometry permits a concentration gradient which is like n of x is equals to n naught cos pi x by 2L between minus L to L like this. So, we have the slab arrangement in which the density, the concentration of charged particles seems to be arranged or following this particular relation. Okay. Now, suppose that I am not writing this text here, I am just saying it so that you can write down or you can grab the context. Suppose the plasma decays both by diffusion and recombination, and assume the rate of loss due to recombination, the recombination rate is minus alpha n square, where alpha is just a constant. Find n, find the value of n at which the rates of recombination and the diffusion are equal. Okay. So, what have you been given? You have been given an arrangement in which plasma is not uniformly distributed, rather following a distribution which is n of x, which is n naught cos pi x by 2L. Okay. So, you can put various values of x between minus L to L and get what is the concentration at each and every point of this particular slab geometry. Okay. Now, the plasma is diffusing from this higher concentration to lower concentration. While it happens, it also undergoes recombination. Recombination is simply electron plus an ion giving you a neutral species, let us say. And at the same time, it is also going through diffusion. Now, we know the rate at which diffusion can take care of plasma. Now, we have to find the concentration gradient such that both these two rates are same. Okay. So, loss due to diffusion is dn by dt. This is equals to d times d square n by dx square. This is what just we did, right. So, since we know the value of n, we can substitute n is equals to n naught cos pi x by L, obtain two derivatives, and then what we get is d times n naught pi by 2L whole square cos pi x by 2L. Okay. Now, this is of course, this multiplied by this is still n naught, right, is still n. So, this is d n times pi by 2L whole square. This is what, this is dn by dt due to diffusion. Now, we have been told that this rate is actually also equal to minus alpha n square. This is by the recombination. Both of them are same. Now, we have to find n such that this equality is valid. So, n obviously becomes d by alpha times pi by 2L whole square. Right. So, n is equals to d by alpha pi by 2L whole square. What is so specific about this form of n? If n follows this distribution, then the loss due to the recombination will be equal to the loss by diffusion. So, both these processes will have the same speed. Okay, right. So, we will try to have one more lecture for diffusion to understand the diffusion process in the presence of a magnetic field in a completely or fully ionized plasma in the next lecture.